Welcome to Unit 6. This lecture video follows right along with your Chapter 7, Section 1 lecture notes. We will introduce the idea of a rational expression and a rational function. A rational expression is a quotient of two polynomials. For example, this is a rational expression. We have a polynomial in the numerator and a polynomial in the denominator, a quotient of two polynomials. In this example, we are asked to evaluate the rational expression when x is equal to -8. We begin by writing a -8 everywhere there's an x. So this expression becomes -8 squared minus 3 times -8 minus 28 in the numerator, and -8 squared minus 15 times -8 plus 56 in the denominator. Simplifying, we have -8 squared, or positive 64, -3 times -8, or positive 24, minus 28 in the numerator, divided by -8 squared, or positive 64, -15 times -8, or positive 120, plus 56 in the denominator. Simplifying in the numerator, we have a sum of positive 60, and in the denominator, we have a sum of 240. Quick way to simplify is to divide the numerator and the denominator by 10, giving us 6 over 24. And since 6 goes into 24 4 times, this simply becomes 1 over 4. In this next example, we are asked to find values for which the expression is undefined. With rational expressions, we have fractions, and those fractions contain variables in the denominator. This produces the possibility of the denominator equaling 0 for certain values of x. And since we cannot divide by 0, there are values for x for which the expression will be undefined. For example, with 3 divided by 2x minus 7, this expression will be undefined when 2x minus 7 equals 0. Adding 7 to both sides, we have 2x equals 7, and dividing both sides by 2, we have x equals 7 over 2. In other words, if x is equal to 7 over 2, we will have a 0 in the denominator, and this expression is undefined. In example 3, we have the same instructions, but our rational expression has a little more to it. This rational expression will be undefined when the denominator is 0, or when x squared plus 7x minus 30 is equal to 0. To solve this equation, we can factor the left side. This is x minus 3 times x plus 10. And using the zero factor property, we find that x minus 3 could equal 0, or that x plus 10 could equal 0. That is, x can equal positive 3, or x can equal negative 10. We found that when x is equal to positive 3 or negative 10, the denominator will be 0, and this rational expression will be undefined. A rational function is a function of the form r of x is equal to f of x over g of x, where f of x and g of x are polynomials. And we of course do not want the denominator, g of x, to equal 0. In other words, a rational function is a function whose formula is a rational expression. Let's evaluate this rational function for x equal to -4. That is, we'll find r of -4. Substituting a -4 everywhere there's an x, we have -4 squared plus 7 times -4 minus 20 in the numerator. And we have 2 times -4 squared minus 3 times -4 minus 15 in the denominator. Simplifying, -4 squared is 16, and 7 times -4 is -28. In the denominator, we have -4 squared, or positive 16, times 2, or positive 32. -3 times -4 is positive 12. And adding in the numerator and the denominator, we have -32 divided by positive 29. So r of -4 is -32 over 29. In example 5, we are asked to find the domain of the function. The domain of a function is all possible input values, all the values that our variable x can take on. We've already discussed that a rational expression is undefined when the denominator is 0. So with a rational function, the domain will be all x values where the function is defined. So we begin by finding the x values for which the function is undefined. This function will be undefined when 2 times x squared plus 9x minus 5, or the denominator, is equal to 0. To solve this equation, let's factor the left side. This is 2x minus 1 times x plus 5. We could then have 2x minus 1 equals 0, or x plus 5 equals 0. Solving for x, we find that x is equal to 1/2, or that x is equal to negative 5. These are the values for which the function is undefined. In other words, these values are not in the domain, but all other values are in the domain. So we want everything else, all real numbers except 1/2 and negative 5. To help us visualize this domain and write it correctly, let's draw a number line. We'll place an open circle at negative 5 and at positive 1/2, and we'll shade everywhere else. Our domain is all real numbers except these two values. So it's like having the entire number line with two little holes at these two values. We can express the domain as all real numbers from negative infinity to negative 5, between negative 5 and positive 1/2, and from 1/2 to infinity. Recall that using parentheses means that we are not including negative 5 and positive 1/2 in our interval. When simplifying rational expressions, the first thing to do is factor the numerator and the denominator completely. Then, divide out any common factors that we find in the numerator and denominator. It's important that we only divide out common factors and not common terms. Looking at the second example, it's very tempting to cross out the x squared in the numerator and the denominator because they are common to the numerator and denominator. Notice that those are common terms, not common factors. We must first factor the polynomials before we can divide common factors out. Let's take a look at 15x to the fourth divided by 12x to the third. Since 15 is equal to 3 times 5, and 12 is equal to 3 times 4, we can divide out or simplify using 3 over 3, which is simply 1. And with x to the fourth divided by x cubed, this leaves us with simply an x to the first in the numerator. So simplifying this rational expression, we have 5x divided by 4. Now let's look at x squared minus x minus 30 divided by x squared plus 8x plus 15. We begin by first factoring the numerator and denominator completely. The numerator can be factored as x minus 6 times x plus 5. The denominator can be factored as x plus 5 times x plus 3. Notice that we have a factor of x plus 5 common to both the numerator and the denominator. Simplifying, that becomes simply a factor of 1. So we are left with the rational expression of x minus 6 divided by x plus 3. One property that often comes up when we are simplifying rational expressions is the idea that the two expressions a minus b and b minus a are opposites. That is, they produce opposite results. For example, suppose we had 5 minus 3. That's equal to positive 2, but 3 minus 5 is equal to negative 2. Because these two expressions are opposites, we know that b minus a is equal to negative 1 times a minus b. Let's take a look at this example to see how this might help us. We begin by factoring the numerator as x minus 7 times x minus 8. And factoring the denominator, this is a difference of squares, or 8 plus x times 8 minus x. Notice that we have a pair of opposites. We have x minus 8 and 8 minus x. They are not the same thing, so we cannot simply cross them out. But if we recognize that 8 minus x is equal to negative 1 times x minus 8, when we simplify, we are left with a negative 1 instead of a positive 1. So we have x minus 7 in the numerator, 8 plus x in the denominator, and all of this multiplied by a factor of negative 1. And that will conclude this lecture video where we introduced the idea of a rational expression and a rational function.